I record every class. Okay, so we've got our crate. Yeah. Right. And then we had 2 ropes. Is that correct?
Yep.
Right. And then what was the force on this rope here?
30.
Force T1. Was it T1 or T2? T2. And that was 30 newtons. Okay. All right. And this is force T1. Was how much?
20 newtons.
20 newtons. And we said this is 30 degrees?
Yeah.
Okay. And what was
100 newtons.
okay, so 100 newtons, so the weight and are we on the ground or not on the ground?
It doesn't look like we're on the ground.
It was on the ground. Okay.
The ground is frictionless.
Yes, ground's frictionless. 0 friction. Okay, weight was 100 newtons, right? Okay. All right, so, Zach, what's going on? Okay. So, at this standpoint, what were my questions?
You said first define the total horizontal and vertical.
I think you said maybe it's FBD. Yeah, we can FBD.
Okay, so FTB was number 1. And then what? Natural force. So 1, 2 is the natural, not natural, normal force, normal. Okay. What else? I asked you if it was moving, right?
Motion of box, direction, and amount.
Okay. So the motion of box, direction, and amount. Okay. Did you all finish this yesterday or for homework? I suspect no one finished it yesterday. I also double suspect no one did it for homework. As I stated, do this for homework. Okay. Not cool. Okay. So so none of you guys finished this problem, right? Okay, so let's finish this now. Let's work on this now. Go. Okay. You got to think about this. Draw your free body diagram. Guys, your free body diagram should have forces in what directions only? Horizontal and vertical. Remember, you got to break that FT2 down into components. Okay, I'm going to pause this. Okay, let's talk about this together, okay? I'm going to shrink this down a little bit so we can kind of have some space. All right. Oops. All right, over here. Okay, let's talk about let's do the first thing, the very first thing. What do we want to do? What's number 1? The free body diagram. Okay. All right. So let's do this. So what do I draw a free body diagram? What shape do I draw? You do a circle or a square. Because it's a crate, I will go with a square. You could draw a star if you wanted to. I'm going to draw a square because it's my free body diagram. Okay. Now, what am I doing with this square? Is that it?
No.
What do I got to do? All right, what are my forces? I got 20. That's F. Here's what you got to do. Don't put the numbers. Just put the variables. FT1, excuse me.
Yes.
Then you have the weight downward, the weight of the box.
F of G.
And then you have the F2x and F2y.
So F2x and F2y.
T2.
Oh, excuse me, FT2.
Oh, yeah.
Okay, what else am I missing anything else? I think I am. What am I missing? Yeah, my normal force. FT2x. I need to assume that there's a normal force. Okay? Here's the strategy on this. You have to determine whether the box is moving up or down, right? That's part of your problem you have to figure out. If it's moving up, what direction is the normal? If it's moving up, do I have a normal force? No. If it's sitting on the ground, do I have a normal force? Yes. If it's sitting on the ground, that normal force is a positive or negative? Positive, right? So, and if it's sitting on the ground, what's the sum of my forces going to have to equal? 0. So if it's sitting on the ground, my sum of the forces is set to equal to 0. I should get a positive normal force. But let's say we don't know for sure just by looking. We have to run the numbers. We can still make that assumption that it's going to equal 0. In that case, and let's say we set it equal to 0, but the normal force comes out to be negative instead of positive. What does that mean? If the normal force comes out to be negative, what does that mean? Yeah, it means that there's excess vertical force, which means that there is no normal force. At that point, the normal force is 0, and the excess vertical force, that normal force is my excess force that is used towards motion. Does that make sense? Does that logic make sense? Anybody have a question about that logic? Okay, Yusuf, question. Andre, any question on that logic? Okay. All right. So we've got that. We've got to then solve for f of n, right? So how do we set that up? Let's set up the equations. Give me the equations. Well, we really have to use these two equations here, right? We're going to have to set up in order to figure out f of n, we've got to figure out these two equations, right? So which direction does Fn work, x or y? Y. So let's set up our sum of the forces in the y, okay? And what are our forces? Give it to me in variables first. Always do this in variables first. Don't plug any numbers in yet.
ft1 plus fn plus ft2y plus ft.
Okay. We're going to make an assumption. We're going to assume that it's on the ground. If we're making that assumption, what is my sum of forces equal? Equals 0 newtons. Okay, and again, that 0 newtons equals my mass times my net acceleration, right? Okay, so let's set up, while we're here, let's set up the other equation. What's the other equation we have to set up? We have the forces in the y. What other equation we can set up? The x. So sum of the forces in the x. What are my forces in the x? Ft2x. Okay. Now, since we're going to have a force, we know it's not going to equal 0, right? So we know that our sum is going to be that force. Okay. Now we can start to plug some numbers in. Do we know what Ft1 is? Okay. So the sum of the forces in the y equals, what's my Ftn? Or Ft1, excuse me, 20 newtons, positive. What's my Ft2y?
15.
Okay, well, how'd you figure that out?
SOHCAHTOA.
Okay, a little SOHCAHTOA action. So Ft2y equals Ft2 times what? Sine of theta, right? And Ft2x equals Ft2 times the cosine of theta, right? So you've run the numbers. What does Ft2y equal?
What is ft2y?
What's Ft2y? 15 newtons, right? It's 30 newtons times the sine of 30 degrees. Okay, equals 15 newtons. What's my Ft2x equal?
15.
So it's 30 newtons times the cosine of 30 equals what? 15 root 3 what? Newtons. Okay. So 20 newtons, my Ft2y is positive or negative 15 newtons? Everybody? Ft2y is what?
15.
Plus 15 newtons. What's my Fn? Don't know yet. We're solving for that. What's my F of G? Negative 100 newtons. And we're assuming that's going to equal 0. That's our assumption, right? Okay, so that's 35 from 165, right? So Fn equals positive 65 newtons. What does that positive 65 newtons mean?
That it is on the ground.
It's on the ground. That we actually have a force pushing up. So we're 16. So do we have any motion in the y? No. Okay. So we only have motion in the x. What's our motion in the x?
T2x.
Well, that's our force.
Oh, motion.
Okay. So that's ft2x. What's the value of ft2x? 28.98 newtons. 25.88. Sorry. 25.98 newtons. What does that mean about my movement? What does that mean about my movement, guys? How do I know what kind of movement? Constant acceleration. Well, how do you know that? Because it equals what? Mass times, yeah, acceleration in the x, right? And the mass is how much?
Well, it's because there is a force there, so it's going to be.
Okay, how do I determine my mass? How do I determine my mass?
I would guess
Where's the kilograms?
You have to convert the newtons to grams for the weighted box.
Well, okay, but there's a difference between.
Wait,
You okay?
you have to divide by the acceleration of gravity.
There you go. So the force of gravity is equal to. That's the trick, guys. You got to figure out your own math. The force of gravity is equal to negative 100 newtons, right?
Right.
Which is equal to my mass times my acceleration due to gravity, right? So negative 100 newtons equals mass times negative 9.81 meters per second squared. That means my mass is equal to 100 divided by 9.81. 100 divided by 9.81, which is 10.19. 10.19 what? What unit, guys? Kilograms. Okay? So now I can use this item, all right, and I can plug that puppy back into here. So that's going to be 10.19 kilograms times my AX equals 25.98 newtons. So my AX is equal to 25.98 newtons divided by 10.19 kilograms. So my AX is what? 2.55 what? Meters per second squared. Now, I could then use this and ask you, after 3.5 seconds, what's its velocity? And how much distance did we go? You see where I'm going with this? Yes. Okay. But I say that, and I know, Sam, you're like, but Sam, I'm going to do that on a test. I'm telling you right now. Be forewarned. I'm going to do that on a test. Dumb? No, it's well, okay. You got to know this stuff. All right. Let's do it. Let's do it. Okay. All right. Okay. Is that cool with everybody? Yeah. Okay. So let's try another new, interesting, fun example. Are you ready? Fun example? Fun example. Okay. All right, here we go. Are you ready? We're going to have... I'm making this puppy up on the fly, so let's see how we go. Well, okay, it's got puppy ears.
That's a tennis ball. It's a tennis ball.
But he said it has to be a puppy.
No, he's kidding. That's like...
It's a pig tennis ball. Okay. Okay. This is a bunch of sand. Okay. Tennis ball is flying down.
Wait, so it's a tennis ball now.
Why does that
Great.
You told me you wanted it to be a dog. All right. Okay, now it's a baseball.
No, wow.
All right. Okay. Okay. Baseball is careening towards the earth, purely vertically. Okay, for the moment. What? Oh, yeah. I get what you're saying. Yeah. Okay, Command C, Command V. Okay, at the end of its run, okay. At the end of its run, it's going to be in the ground.
Looks like there's two.
Okay? There are two tennis balls because I'm going either before and the after. Okay? All right. And we're kind of doing one of these things. Okay? Let's say the mass of the tennis ball is, or the baseball, let's give it 1.2 kilograms. It's a pretty heavy baseball. All right? Pretty heavy baseball.
That's a lot.
How many grams is a baseball? 500 grams? 50 grams?
I don't know, but it's not. This is like the most water left
145 grams. There we go. All right. I know I was way off. I just figured. Okay. All right. 145 grams. Okay. Let's say that it embeds itself into the sand. It's going to embed itself into the sand. Let's say, let's do 20 millimeters. Okay? It's going to embed itself in the sand. Okay? It's going to embed itself in the sand in that scenario. It's going to do that in 0.02 seconds. Okay? It's going to come to full rest at 0.02 seconds. From when it touches the from when it touches the sand, it's going to embed itself in there 0.02 seconds. Okay? Okay, I'm thinking for 1 second. Hold on. And I'm going to, let's say that its final velocity, V ball final, is equal to 100 meters per second. Okay? I'd like you to tell me a couple of things. I'd like you to tell me the, actually, let me take that back. Take that back. I'm going to tell you, I know. You're like, well, Mr. A. I know. Oh, I most certainly can, and I most certainly did. All right.
We can't do it as easily.
Oh, you can. Okay, all right. Let's see, at 50 meters, okay, the velocity at 50 meters, okay, is negative 75 meters per second. Okay? What I'd like you to tell me is the impact force that the ball makes in the ground. What's the impact force it makes? All right? Go. What's my impact force? All right, let's go ahead and do this together. Okay, ultimately, I'm looking for the force of impact, right? Okay, what does my force of impact equal? What's it equal?
What?
No. Give me an equation. Never give me a number. Always equations first. Mass times acceleration. This acceleration is from where to where? Guys, where's my acceleration for? In the force.
Contact to the ground to the 20 millimeters.
From contact to stop. That's my acceleration rate. Right? You guys see that? Okay. So I can calculate this a couple of ways. What's the first way to calculate acceleration? Hello? Okay, delta V over delta T, right? And what's my delta V?
It is.
How do I break it out? Oh, how do I break it out? Variables first. How do I break?
7 or something.
V final minus V initial over delta T.
6.27.
Hold on. So what's my final velocity? What's my final velocity? No, during the deceleration point. 0 meters per second. Minus my initial velocity over my delta T of 0.02 seconds. That's my acceleration rate at the ground level for contact. Does that make sense?
Yeah.
Okay? So you can solve it that way. Okay? So I need that initial velocity. I need that velocity up above, don't I? Okay? How do I figure the velocity at that initial velocity for deceleration, which is what? My final velocity.
Velocity for the fall.
For the fall, okay?
So we're like almost there.
You're almost there. You're almost there.
Done.
Okay? So how do I figure out my final velocity from here to here? Everyone with me? How do I figure that out? Girls, what do I do? Girls, how do I figure that out, right? Because you guys see where I'm going with this? Yeah? Okay. Okay, so what's my how do I figure my final velocity? So for the fall, this is all for the impact. Stop making those noises, please. Okay, cut it out. You can, if you knock again, you can knock in Mr. Gunnan's office next. Okay. For the fall, what's my initial velocity for the fall? Negative 75 meters per second. What's my final velocity for the fall? Don't know, but it's the same as my initial velocity, right? Okay, what other information do I need?
You also need how long it takes to burn.
Okay, so I have my delta t that I need, right? Or I could possibly have, don't know if I need it yet. What other possible variables do I have? Distance, my y initial, y final, and my acceleration rate due to gravity, right? Or in the y direction, right? So my delta t, do I know my delta t? No, I don't. What's my y initial? So my y initial? 50 meters. What's my final? 0. What's my acceleration rate? Negative meters per second squared. Now, if I've got this, I can say Vf squared equals V initial squared plus 2a delta d, right? So I have my V final, which is what I'm looking for, Vf squared, or Vf, equals a square root. What's my V initial? Negative 75 meters per second squared plus 2 times my negative 9.81 meters per second squared times my delta distance, which is what? What's my delta distance? Negative 50, because it's down, right? Hold on, guys. So I can solve that for Vf, which is my Vi, put my acceleration, there you go. Make sense? I don't know what the answer is. What's the answer, guys? What is your answer, Sean?
We got 589.